Okay, I think we're live. Hey guys, this is a code walkthrough for Mellow Flexible Vaults competition on Sherlock. We'll wait for a couple of minutes before everyone will join, and then we'll start. We have Andre here.
Hey everyone, hey.
Yeah, maybe some of you guys already know him. So yeah, the current plan is that we're going to have a code walkthrough for Mellow Flexible Vaults competition. We'll wait for a couple of minutes. Everyone can join and enjoy this beautiful code walkthrough. In the meantime, maybe Andre, you want to share some like insights or the history how you came up with this pretty interesting code base for flexible vaults.
Well, that's a good question. To start with, I believe the general problem, the general issue that we have while trying to curate user funds is the like question between do you want to build a system in centralized way or decentralized? But if you are building it in decentralized way, you are losing the ability to flexible change or add different external protocols in the system to like actually expand it to different, even sometimes off chain taxes in some case, or to build it freely cross chain. And that's why we have decided to build such a system that allows us to do everything of that, while we definitely lose some amount of like decentralization in our project. We still have really high level of automation in it, and and the like curator, the actor in our system who is actually responsible for managing funds, cannot do any arbitrary actions. So he is only able to do what we allow him to do. Like we I mean, admins of the vault. So uh, the idea is that we are trying to reduce the like unwanted actions from the curator side while he managing his funds of the users in the vault. We still want to have this system as a liquid vault. That means that users deposit liquidity assets in the vault and receiving for this some corresponding amount of shares. And we also have a withdrawal redemption flow for the opposite process. And yeah, that's the basic idea. The only tricky part that arises while we're trying to do this like really flexible system where a curator can delegate liquidity into different protocols, chains, and even maybe off-chain entities such as taxes, NPCs, or other entities. The problem is that it's really hard or sometimes even impossible to evaluate the price of the vault entirely, and that's why we just was forced to use our centralized oracle in this system, while it still can be in one way or another. While we still can make it slightly less centralized by introducing, like, I don't know, zk proofs or different other approaches here, it's still really critical and like critical part of the system, and it is bottleneck in terms of decentralization. But still the system works pretty smoothly. Even with this centralized oracle, there are a lot of checks to prevent like random updates of the prices that can be malicious in some way. So yeah, that's the idea.
That's cool. That's cool. Thanks for sharing this. Yeah, I think we already have 80 people here. I think we can start. Essentially, yeah, to sum up, who for everyone who just joined, this is a code walkthrough for Mellow Flexible Vaults scope. We started the competition yesterday on July 14th. It will run for 2 weeks. Thanks for Mellow. They increased the rewards to 70,000 in total.
And most importantly, decrease the code size as well. So yeah.
Yes. So that's really interesting. And if you're a security researcher, we highly advise you to join the competition and try your best in finding as much as possible. Um, yeah, essentially, yeah, 2-week competition. Please, for this code walkthrough, feel free to ask any questions in the Twitter chat. So I think we can answer questions during the walkthrough and in the end. So yeah, please feel free to ask. We see all the questions here, or in the Discord after you, if you will watch the code walkthrough in the recording. Yeah, I think I will let the stage to Andre so we can start the walkthrough itself. So please, Andre, stage is yours.
Great. So can you see my screen right now?
Let me share it. Okay.
Yeah,
Yeah, I
great.
think we can see it.
Yeah, perfect. Okay, let's start with the schemes, with the overall overview of the system and how it's and which components we have in the system. So basically, the core contract that we have is the Vault contract. While it is a combination of different modules, it's still the central part of the system, and all other elements are connected to it. As you might see here, we have not only one vault who holds all the funds in the system, but also we have a system of sub vaults where, based on the different risk limits, different permissions, trusted entities such as curator or uh, or using different hooks that we have in the system, funds can be transferred from the vault to the sub vaults, where they are actually delegated into the external protocols to generate some yield. Also, important part is that we, as well as these sub vaults and a vault contract, we also have a 3 different manager contracts for managing shares, for risk managing, and fee management. So share manager is a contract that actually mints and burns user shares, uh, controls all the parameters regarding different lockups, different policies like deposit, like mint, burn, or transfer, different whitelist as well. Yeah, so we have 2 different implementations of this share manager, the tokenized one and basic share manager. Basically, the only difference between these 2 implementations is that tokenized version is ERC20 compatible. So we have all these ERC20 methods like balance of, allowance, transfers, etc., while basic one does not have any of that. So yeah, that's the only difference between these 2 managers. The next thing is risk manager. Risk manager is a contract that is responsible for managing vault limits, sub vault limits, allowed assets in sub vaults, and that's pretty much it, I believe. Fee manager is obviously a contract that manages all the fees that we have in the system, like deposit, redeem, performance, or protocol. While protocol could be also named as a management fee, but it's still the constant percentage that we are getting from all the stake per year. So yeah, that's the idea. And we also have a centralized oracle that I just mentioned before. This is a critical part of the system that actually responsible for pushing information about vault price to the vault. So the problem with the reason why we have this oracle, once again, is that once we start delegating in different protocols, maybe even cross-chain, maybe even into MPCs and off-chain sexes, we're no longer able to efficiently evaluate the vault price. So here we came up with an idea that we have to do this solution with the centralized oracle, where we just collect in off-chain bot all the required LP prices of the vault, and we submit them each day, for example. And based on these prices, a lot of different components of the vault properly work. Yeah, due to this strange like behavior of the oracle that we on the updates is like once a week or once a day, sorry. We cannot say at a time that what is the like exact TVL of the vault or what is the exact TVL of the sub vault. So that's why when we're setting any limits by the risk manager, let's say we want to set the vault limit to I don't know, 1,000 Ethereum, then if we reach this limit and the liquidity inside the vault reduced due to, I don't know, slashing events in symbiotic protocol or some other actions, or, I don't know, impermanent loss on DEXs, then the system still thinks that this limit is still 1,000, like the current TVL is still 1,000. So the no new deposits are allowed in the system until a trusted curator or admin of the vault comes and decides to like manually reduce the like balance of the vault, this like stored value of the balance in the system. Yeah, and we obviously have different deposit and redeem queues in the system. There are actually two sets of them. The first one is quite simple for explanation. It is just a delayed version of queues where user, in case of deposit queue, users request their like will to deposit assets into the vault, and after some time, with the corresponding Oracle report, these requests are processed and actually transferred to the vault and to the sub vaults. Pretty much the same thing happens in the redeem queue, where funds like not funds but users requests like amount of shares they want to withdraw from the vault. After some time, with the corresponding Oracle report, these requests are handled, and also there is some there is also another important thing, that upon handling withdrawals by the Oracle report, redeem queue does not allow users to claim funds instantly. There is separate handle reports handle batches function that is needed to be called to pull actually funds from vault to the redeem queue. But we'll talk about this later when we will go to the code base itself. Yeah, and we also have a set of queues for permissions, deposit, and redemptions. Here, the idea is that a trusted user goes to our consensus contract, where he, not actually a consensus contract, but like consensus set of signers, where he collects all the required signatures to do the deposit or withdrawal or redemption from the system. Once he got all the required, like once he got this threshold of the signatures, he is actually able to do instant deposit without waiting for an Oracle report, or instant redemption based on the current amount of liquid assets in the vault in the system. And yeah, also important thing to note here is that, as I mentioned before, in a fee manager we have deposit, redemption, and two other type of fees. While they are applied for deposit and redeem queue, they are not applied to the signature deposit and signature redeem queue. In most cases, we might think about the user of this signature deposit and signature redeem queue as like a trusted user, for example, in some cases, or a trusted arbitrageur. So the idea why we have this like separate flow is to allow, like, as we know, if we are using this on only these two queues, there is some delay between the time when user deposits funds and into the queue and the time when he receives or corresponding amount shares for this deposits. And it's not that good while in case if we have any external liquidity on dexes. So for example, we have a shared token of this vault, and we have a pool on Balancer, for example, and for some reason, due to some big swap on this pool, the price deviates from the expected one, from the honestly reported by the Oracle, for example. And in this case, we can allow some arbitrageur to come to the vault to do these deposits to instantly get shares for the corresponding amount of assets to move the price on this DEX pool back to the normal state. Yeah, that's pretty much it. If we're talking about like brief overview of the whole system. Now let's talk about subvaults. As I mentioned before, the liquidity, once user deposits liquidity into the vault, into the deposit queue actually, and this liquidity is transferred to the vault, it can also be transferred not only to the vault contract, but to the sub-vaults. These are vaults as well, but with the different set of functions and stuff that they can do. So yeah, let's go to the sub-vaults, and here we have this quite complex schema. Here is the idea that upon deposit into the subvault, a trusted actor such as curator or strategy contract, we can think about strategy contract in the same way as about curator. There is no difference between them. This trusted actor can actually delegate the funds from the subvault to different external protocols by calling call function in this subvault. This function is implemented in call module, obviously. Here we have 4 different parameters in this function, like where if this is an address of the external contract, value is the amount of Ethereum or like native token that will be sent to this where contract upon the call, and at the moment of the call, and date is the date of the call date of the call, and payload this is a verification payload. This is our custom thing, and the point of using this payload is to verify that this curator has all the required permissions to actually do this call. So after sending this call function, after sending this call request to the subvault, actually just calling this subvault with the call function, the verifier after that verifies that the curator has all the required permissions. Based on the payload verification type, there might be 4 different types of verifications. These are not them. And basically, we have 3 types that, let's go to the code so I can show you this. So we have these 4 different types of verification that we have in the system. This is on-chain verification, Miracle Compact, Miracle Extended, and Custom Verifier. So basically, depending on which type is specified in the payload, one of the following flows will occur. So if we have on-chain compact type of verification, then we just calculating this hash of the caller, which is curator address, which is the external contract address, and the selector of the function that is that will be called, and we just checking that hash of this bytes of these bytes are existing the compact call hashes set, which is set by the trusted actor in the verifier contract itself. Let's probably go deeper to the implementational aspects of this. So yeah, basically once we have this verification type, we're just checking that these parameters hashed with the described function that I just mentioned here is present in the corresponding hash set. So we can check that corresponding rights are granted to the curator to do such call. This is the most simple one of 4 different types of verifications. The next 3 actually require not just the verification type, but also the miracle proof to get information about the, like, whenever we have these data verification payload in the system or not. So after we are proving this by calling corresponding miracle proof with the miracle root that is set by the admin of the vault. After that, we are going with the next step of the verification process. We have 3 remaining types of verifications. The first 2 is miracle extended and miracle compact. They're pretty much the same, where in both of them we hash in miracle compact we hash the same parameters as in the easy loads. Like in on-chain compact, we just hash the caller of the contract, the external address of the external contract where this call directs, and the first 4 bytes of the call data. That's it. And we check that the verification data that is also passed into the payload is equals to this hash. So basically, why we know that it's not just an arbitrary hash that is passed in this verification call, it's because we verified it against the miracle root in here. For extended miracle extended type of verification, we just hash the whole call with not only with who and where, but also with the value and the full data, which might be quite expensive, but we assume that there won't be any such calls that leads to out of gas error or something like this. And we once again check that this hash of this structure equals to the expected verification data. We just extract byte 32 from it data anyway. And the last one, the 4th type of verification, is a custom verifier, where we have information about, like, verifier address in the verification data, and we are doing this external type of verification in external contracts. Currently we have only 4 of them, as you can see here. Basically, let's start with something simple as ERC20 verifier. And custom verifier, we just check that the corresponding parameters are trusted in one way or another. So, for example, when we are verifying the call to ERC20 contracts, such as different tokens, we might have only 2 different functions, mutable functions here, like approve or transfer. We check that the selector matches. We check that if the call is transferred, then the amount of assets that we want to transfer, actually, that the curator wants to transfer, actually is non-zero. We also check that the address to which one we do this transfer or approval is trusted, as well as curator, as well as asset. So we are doing a lot of checks here. Quite the similar happens in the eigenlayer and symbiotic verifiers. We just do a lot more checks here due to all these different types of functions that can be called in symbiotic or eigenlayer protocols. The next thing that we have here is bitmask verifier, which is quite complex to understand probably, but the idea is that all calls are encoded as can be encoded as a bytes array, where the first 32 bytes corresponds to the caller of the address or curator. The next 32 bytes are where, like, target external contract. Next are value that we want to send to this external where contract, and they call data, obviously. So basically what we have here is like bitmask matching. So we just doing in simple words, we are calculating this encoded data, and we are doing bitwise AND between these data and corresponding bit mask, which consists of like zeros and units, obviously. And yeah, we just hash the resulting array with some hash function, and we check that the corresponding hash equals to the expected one. So this way we can implement actually all the logic from ERC20 verifier. For example, here we don't want to really check that the amount of let's exclude this check where we check that the amount of assets that we want to transfer is non-zero, and let's say that we just want to check that the caller is trusted, that the selector is trusted, and that the recipient of the tokens is trusted as well. In this case, we can just set who to all units, like 256 units here. The same here. The same thing for where and value part of the bit mask, and for call data, for the data part, we just mark with units only first 32 bits of the bit mask, and the remaining 256 bits will be marked as zeros, because we don't really care about the amount of assets that we want to, like, that curator wants to deposit or approve, not deposit, to transfer or to approve to some other external contract. Yeah, so this way it's quite powerful thing. This way we can almost certainly verify almost all calls to the external contracts where we don't have anything anything like dynamic arrays or bytes array, or I don't know, strings or different other dynamic structures. With this verifier we can verify all the remaining types of calls. Yeah, that's pretty much it regarding permissions. Okay, let's turn back to the schema, and here we have a flow where curator wants to do some external call to an external contract. He passes information about like the data, the value, and the verification payload. Based on this data, we have a call to verifier where all this is verified based on the verification type, and if the verification type is custom verifier, then the verification goes further to like custom verifier itself, to this contract. And yeah, if the verification is successful, only after that the subvault calls external contract with the provided by the curator or strategy data. Yeah, that's pretty much it regarding how we have how permission setup is set in subvaults. Now let's go to the like module configurations. So as I mentioned before, we have like two core elements in the system. This is a vault and a subvault. Both of them are configurations, let's say it this way. That means that they are configured with some set of modules underneath. Basically, vault is inherited from the vault module and share module. The subvault is inherited from the call module and subvault module, and etc. etc. Yeah, you can see here how all this corresponds to the like managers, oracles, and verifier contract. Yeah, that's probably it. Yeah, I will share all these docs later. I will add them into our documentation later. Currently, they are only available here. Okay, let's then go to the code base to start actually code walkthrough. So as I mentioned before, we have these two vault and subvault contracts that we just saw on the graphs in Excalibur before. Yeah, here we have a vault contract, which is a configuration that is constructed from vault module and share module. We have all these initializers and setup flows here. We also have a vault configurator contract that allows us more easily to set up all the required parameters in the system without need for like doing it by our hand each time, like some automated deploy script, let's say. Yeah, the next important thing is probably share module, share manager. In share manager, we have a lot of logic implemented to control user shares, to know what amount of shares is claimable and what amount is active, like actively corresponds to the active balance of the user. Yeah, and all other functions here are used specifically for managing all this share logic. We also have quite interesting thing as flags in this share manager. They are used to store critical information about pauses. Oh, sorry, different library. About pauses in the system, about different lockups in the system. So here is a description of what's actually happening here. TLDR, we just packed everything tightly into one uint 256 to store all the data in one place to actually efficiently get information about all the required flags upon at the moment of the deposit, withdrawals, or maybe transfers of this share tokens of the vault. Yeah. The next thing that I would like to discuss is probably Oracle and how it is built. Yeah, as I mentioned before, we have a trusted trusted actor who actually submits reports about asset prices. The important thing here is that the report the price that we use in the system is not the usual one. We just use the reversed price. That means that let me go to the Oracle and Oracle. That means that the actual price is properly used in this way. So we multiply amount of assets by the price to get the amount of shares that we would have to upon like deposit or some other actions in the system. That's why, for example, when we are calculating performance fee of the vault, we are looking not on the growth of the price, but on the reduction, falling of the price with time. So yeah, please take a look at this implementation. It's quite important for better understanding. Yeah, the next important thing that we have implemented in this vault is security intervals. So for example, as I mentioned before, we have a trusted Oracle that reports prices, and we in some way calculates these prices in off-chain. Obviously, with enough effort and resources, someone would like to hack this off-chain Oracle in a way that the reported price can be somehow manipulated. So, for example, the side attacker wants to, for example, somehow manipulate the off-chain bot, so the price that will be reported can actually fluctuate from the actual honest estimation. And to prevent this, we have these two different intervals, deposit interval and redeem interval. That means that only requests that were made before these specific corresponding timestamps will be handled by this or like some other reports. And in this way, we increases the gap between the moment when user makes his deposits into the system and the moment when this user can claim his funds from the deposit queue. Thus, we are preventing or drastically increasing the prices of possible attacks on the oracles. yeah, so we think they are no more a threat for our system due to this like logic implemented here. Also, important thing to note is that upon submitting Oracle, we checking that the price that the trusted actor submits into the system is within expected boundaries. So, for example, okay, so let's just go to the function that actually checks all of that, and this function is called validate price. Yeah. What's happening here is that we have two set of boundaries for the price. We compare the current price for the specific asset to the price to the same asset from the previous report, and we obviously have some deviations, some difference between these prices. We have maximal, absolute, and relative deviations that which represents the like maximal amount by which the price could move between two reports for this specific asset, and if the price lies above, like fluctuates even more from these boundaries, then we just reject this report with an error, and we're not allowing this price to be reported in the system. Yeah, and we also have not only like maximal boundaries, but as well, but also suspicious boundaries. The idea behind this is, let's say we have maximal boundaries set to, I don't know, 1%. And let's talk about relative boundaries at first. Let's say we set these max boundaries to 1%, so the deviation from the previous price cannot be higher than the 1%. Otherwise, we will just revert this attempt to submit report in the Oracle. And we might have not only this, but also suspicious price that can be, for example, something like 0.1%. So we assume that the price of the vault cannot fluctuate more than 1% in any circumstances, in any cases. That's why we have these like maximal boundaries, but also we have this suspicious boundaries to prevent any like suspicious behavior of the actor who reports the prices. For example, if the price deviates more than to 0.1% from the previous one, we say that, hey, this report is suspicious and we should take care of it on behalf of the trusted actor, such as admin or some other trusted entities. So once we mark this report as suspicious, this report won't be pushed to the queues to actually process all these pending deposit requests and withdrawal and redemption requests. So to actually accept this suspicious price, we have a separate function in the Oracle contract, which is called obviously accept report, where we pass all the information of this suspicious report. And once this function can only be called on behalf of the accept report role. On behalf of the actor with this role, and after accepting this role, the actual report is pushed, and corresponding to it requests pending requests in deposit or redeem queues are handled automatically. Yeah, that's probably it about Oracle. It's quite complex, but still, I think it's pretty straightforward still. Yeah, the next important thing to discuss is, let me think. Let's start probably with something simple as Fee Manager. In Fee Manager, we just have different, this is an ownable contract, and we expect to deploy it for per vault case, not just like one entity for all vaults. So here we have different parameters that represents information, a different function that represents calculations with the fees in the system. All fees are denominated in D6 format. So yeah, basically to calculate deposit or redeem fee, we just apply this fee to the amount of shares that user wants to receive or to withdraw upon redemption. And for calculating all the remaining type of fees, that means that protocol and performance fees, we use this calculated function because we just don't need to use anything else. Here we actually calculate the price deviations from the minimal price to the current price. We calculate the amount of time spent since the last last time we calculated these fees. And we just multiply it by the protocol fee, etc., etc., etc. Obviously, if we are doing this calculation, we also need to update the minimal price and the timestamp when we when we calculated all these fees. And for this, we have permissionless update state function, which actually updates the information about vault parameters such as the timestamp when these fees were claimed last time and the minimal price of the vault in the base asset. So to calculate all these fees, I mean, I'm talking about performance and protocol fees, we need to have these base assets set for the vault. So for example, if our vault works with different assets such as Wrap-Staked Ethereum, we can use our LRT with P2P, for example, or some other assets. We can evaluate all these assets. We can have set as a base assets, for example, Wrap-Staked Ethereum. So only upon handling these reports corresponding to this Wrap-Staked Ethereum, we will actually apply all the fees in the system. And that's probably it regarding fee manager. Let's go to the risk manager. In the risk manager, we have, obviously, as I mentioned before, we have different limits to control risks between different subvaults and the vault itself. We also have information about allowed assets that can be pushed to the subvaults to actually start delegating from them. And that's pretty straightforward. We have signed arithmetics here, but it's still quite simple, I believe. And what I mentioned before is that once we reporting the price of the system, we no longer can say that the vault TVL or sub-vault TVL is the exact amount of balance that we have here, because upon such, between in the time between the last report and the current timestamp, there might be some additional yield can be generated to the vault, or something opposite, like slashing events or impermanent losses. And this is why we cannot say for sure that this balance is quite accurate. And that's why we also have these two functions that can be called not just by the vault or queue contract but also by the trusted admin or curator to actually slightly fix these balances to make it more accurate. That's probably it about risk manager. As I mentioned before, basic share manager and tokenized share manager only differ in terms of the ERC20 interfaces. Basic share manager does not implement them, but while still use the same storage slot as ERC20 upgradable from OpenZeppelin implementation, just to make it possible to migrate them from one to another at any time. That's probably it. Okay, the next thing that we need to talk is modules. We have quite a lot of modules here in the system. Let's start with the base, verifier, and call module. Base module is quite simple. We have some auxiliary functions to receive native token of the chain, to receive NFTs if they are transferred with the safe transfer call. And we also have a low-level function to get information about specific slot. This might be very useful for different upgrades to check that everything is as expected. Yeah, and that's probably it. The next thing that we have is verifier module, where we just where the only function, the only public function is verifier public view, which returns a reference to the verifier contract. And yeah, that's it. And it's this verifier module also inherits from the base module, so nothing is unexpected here. The next module that I'd like to discuss is call module, that is used in the subvault actively. This is the core module that helps curators to delegate, to interact with external protocols, to delegate liquidity into external contracts and to interact with them in this way. We use this verifier from the verifier module here to verify that the call is properly configured with the payload, verification payload, and that the curator that calls this function is actually has all the required permissions. And after verifying this, we actually do the call with the value, possible value. Yeah, that's it. Okay, next thing that I would like to discuss is share module. And that's where the things gets quite complex. Yeah, here, this is a module that is responsible for managing all the deposit and redeem queues, like to create them, to remove them, to this module also responsible for setting and controlling all the hooks that we have in the system. Currently, they are only used upon handling deposit requests or withdrawal requests in deposit, redeem, or redeem queue, both and for signature queues as well. The next thing that we have here is queue limit, and this is quite interesting thing that, like, it's easy to say that once we allow anyone, like a trusted actor such as curator, to create deposit queues in the system, the things might get quite complex when the amount of these queues grow unexpectedly to an unexpectedly large number. For example, hundreds of them. I don't know, for example, malicious curator or something like this. And in this case, users will not be able to claim their shares due to the logic implemented in this module. The idea here is that we want to allow like lazy propagation of the shares upon deposit. So once user deposited his funds into the deposit queue, this user does not need to do anything else to claim the shares after the report arrives with the proper timestamp. So we just calculate the shares of the user in like lazy way. We just iterate over all deposit queues that we have in the system, and we simply increase the his shares to that number that we have here. Yeah, and yeah, that's why we want to limit the amount of queues that can be deployed in the system by calling this create queue function. This is a like single function that is used for creating deposit and redeem queues based on the flag that we pass here. We also have some logic implemented for factory contract that allows us more easily to deploy different instances of trusted contracts with trusted implementations. Yeah. So yeah, here it is. This is the function to claim all the all the shares from all the deposit queues that we have in the system currently. Here it is quite simple, and we just iterate over all queues for all assets. Yeah. We also have the function for handling report from the Oracle. So once the Oracle receives the report from the trusted submitter of it, the Oracle validates that the price of this that is set in this report is properly corresponds to the previous reported price, and if it's so, then the Oracle calls this handle report function. We can see here where the funds and fees are calculated. Yeah, the next thing that we have here is yeah, that's probably it for share module. It's quite complex, but mostly consists of few functions, so no need to be extra careful with it, I believe. The next thing that we have here is vault module. Vault module is responsible for managing all the subvaults, and it is used in vault contract itself only. We have some pagination. We have some functions to iterate over subvaults, reference to risk manager, function to create, to disconnect, and to reconnect subvault to the system. The idea behind these three functions is, the first one obviously is to create a subvault where we set a specific verifier with predefined permissions, so the curator can actually do some stuff in this subvault to, for example, delegate liquidity into external protocols. The next two functions are used specifically to like the first one is used for disconnecting subvault from the system. It's worth mentioning that the idea behind this function is to like remove the subvault that we are no longer use. All the checks about like liquidity and balances should be done before calling this function. But even if there is some liquidity left on this subvault, it might be a proper way to call these functions, because in any case we can transfer the funds from the disconnected subvault back to the vault contract by adding new permissions into the verifier, or by reconnecting it using this function. It's also worth mentioning about reconnect subvault function is that this function not only reconnects vaults that were previously disconnected by calling this function, but also this function can connect the vault that were just properly configured. So that means that the subvault and the verifier of these contracts are correct verifiers. That means they are deployed with these corresponding factories, and that the vault address set in this subvault module and verifier are set to the address of this vault. Yeah, and if everything is all right, then we just adding this subvault to this set of subvaults. Yeah. The next thing that we have here is two sets of functions for pulling and pushing liquidity from and to subvaults. We have first two function sets are typically called by a trusted curator. We have done reentrant modifier here, and we also have two functions for hooks, which are called through delegate call in the vault contract directly upon handling reports, pending reports from the queues, or like actual reports in signature queues, actual requests in signature queues. Here, as you can see, we don't have any modifiers except of the check that the sender is addressed this. Yeah, all right, that's probably it for vault module. Let's talk about subvault module. It's quite simple as well. Here we have a reference to the vault contract that is set upon initialization, so it cannot be changed later. only except for the case when we would like to migrate the subvault contract implementation to the new one, but it's unlikely, and it's definitely out of scope currently. And we have the only one function here, which is poll assets function, which can be called only by the vault itself, and this function transfers all the requested funds to the vault, back to the vault. Yeah, that's it. Okay. Next thing that I'd like to discuss is probably, okay, we have already talked about managers, oracles, permissions, queues. Let's start with signature queues because it's quite simple, I believe. Signature queue contract implements YEP 712 standard, where we have an off-chain signatures that are sent to the consensus contract and verified there. We have all the auxiliary functions to actually generate these signatures in off-chain, and we have also a lot of checks to actually validate that everything is properly configured here in this order that user wants to send to actually get the shares for deposit or to withdraw shares and to instantly get some amount of assets for that. Yeah, that's it. We have some additional checks here that even if the order is trusted and generated in off-chain with the trusted consensus, we can assume that consensus cannot be compromised because it's just how it's worked usually. And even so, we have this additional check that the price that is sent in this report is valid price and it is not suspicious. So we check it against Oracle even here. Yeah, that's it. Okay, next two contracts that we have in the system is signature deposit and signature redeem queues. They implement only one functions each. For deposit and for withdrawals, the flow is quite simple. We, as a contract, get information about order that user wants to execute in this queue, and the set list of signatures. We validate that everything is properly configured in the signatures and order. We increase nonce for the caller, which is message sender of this function. And we do different stuff based on the implementation. For deposit, we are going to transfer assets from the user address to this address. After that, we are going to send funds from this address to vault address. Actually, I think we can do it in one call, but anyway, we also have a call to the hook, which is executed properly because it is determined in this share module based on the address of the queue, and each queue is marked with the is deposit queue or not, and based on this we are getting proper hook. There might be the cases that there are no hook at all set for the queue, even default one. This is expected behavior as well. In this case, curator needs to push funds directly to subvaults by his hands by calling push assets function or pull assets. Yeah, and we also increasing all the parameters in the risk manager related to modifying balances in the vault. And yeah, we means corresponding amount of shares to the user. Quite the same thing happens in the signature redeem queue. Yeah, don't think that it's worth mentioning here. And now finally we have queues. These are the most complex contracts in the system. Yeah, and once Oracle receives the report from the trusted submitter of the reports, this report is pushed to the share module, and from this module, this report pushed to the queues. It's queues where these the next process occurs. We check that all the parameters are like at least somehow valid, that the price is non-zero, that the timestamp is in the past, because we have this deposit interval or redeem interval to prevent all these manipulations with the Oracle. And based on the implementation, the different processes for handling withdrawals occur. And let's start talking about deposit queue then, because that's it probably for base implementation of the queue. Now we have to go to the deposit queue contract. Yeah. The idea of this contract is to allow users to create pending requests in the system. So for handling this request by the Oracle, user will receive some corresponding amount of shares of the vault. We also have few restrictions in here. The first one is that we are not allowing reports from, or I mean, like, we're not allowing multiple pending requests for the user. So if user wants to create new deposit requests, he needs to cancel previous one and create a new one. We have all the related functions for this. And obviously, as I mentioned before, for part with the secure intervals, we want to prevent any reports to be handled there that are too close to the report timestamp, Oracle report timestamp, to prevent any possible manipulations. That's why we use FenWick3 in this contract. Yeah, I'm not quite sure that it's worth mentioning what's happening in FenWick3, but it is. We have a documentation for it, and it is interesting. Just let me see. Artemi, can you hear me?
Yep.
Okay, so it's just a GitHub then.
Yeah.
Well,
yeah,
that's
it's just to show to GitHub. Yeah.
Yeah, got it.
No worries. We're still live. So
yeah, good. Okay, so we have this FenWick3 library, which implements zero-index FenWick3 binary indexed tree. The only difference from the default zero-indexed implementation is that we only allow tree with sizes of the power of 2 to make it very easy to extend it in twice, because we just push the latest element of this tree to the new to the new latest element of the tree, and that's why we don't need to spend a lot of gas to actually extending this tree. Yeah, this tree stores signet prefix sum on an array and can modify it in O or its logarithm of n, where n is the size of the array, like it's mapping, but it's still the same. Yeah, that's pretty much it. And we have a get function for this tree, which returns the sum on the sum segment of the array. Yeah, that's it. Let me see. Sorry, I'm quite. Yeah. Obviously, this is the function that we're calling in the deposit queue contract. To make it simple, I don't want to go deeper into the implementation of the FenWick3 that we use here. The only thing that I would like to mention is that for get function, we use inline assembly to make it slightly faster and cheaper for users, because it's crucial for us. So what's happening here is that upon deposit, user sends the corresponding amount of assets to the system. We also have Merkle proof if we have Merkle whitelist enabled in share manager, and if it's so, then we validating it against Merkle root. We're also checking that the user is whitelisted by the in fact, we have like two different whitelists in the system at the same time. We have a mapping whitelist where we just directly store all the required information in the just usual address to bool mapping, where we check that if we have this flag flag that shows us that we have this on-chain whitelist enabled, then we check that the user is in this whitelist, and we also have a Merkle whitelist. So if the Merkle root is not 0, then we are going to check that the Merkle proof and validate that the sender is in the allowed whitelist group. So the tricky part here is that, in fact, these two whitelists work in at the same time. So there is a possible scenario where we might have this whitelist enabled at the same time. And in this case, user needs to be in both whitelists at the same time to be able to deposit. So in on-chain mapping and in Merkle tree whitelist as well. Yeah, that's probably it for this part of the function. Yeah, the next thing is the handling of the deposit request. Upon such request, we update the state of the tree. We update information about the latest timestamp when user requested a deposit request, and etc. etc. All other information are updated here, and we also update information about pending assets in the vault to control that to control all of this limit stuff in the risk manager contract. Yeah, for cancel process, it's quite simple. We just do the opposite of what is implemented in the deposit function. Yeah, we just get information whenever this report is claimable or not, and based on this, we revert if this request is already claimable and user can claim it but not cancel. Yeah, we also have a claim function that I will explain later. But basically, we trying to find with the binary search the corresponding price to this report, and based on this price, we just calculating amount of shares for the user, and we are doing all the remaining logic here. Yeah, that's it. Next thing, this is the most difficult and the most important part of the deposit queue, which is quite complex, I believe. It is a handle report function. It's an implementation of this function, of the abstract function from the queue contract. Yeah, what's happening here is we are determining at which assets will be handled by this report, by this Oracle report. This timestamp corresponds to the, like, if we submit report and it is correct in terms of suspicious boundaries and max boundaries, then it is directly instantly pushed to the consequently to the deposit queue, where it is where this timestamp corresponds to the current block timestamp minus deposit interval. Or if we have this suspicious flag on the report, on the previous report, and we mark it as non-suspicious by accepting it on behalf of the trust detector, this timestamp will be even lower, corresponding to the actual timestamp when the corresponding Oracle report were created, and minus the deposit interval once again. So yeah. And what's happening here is we're just calculating information about how much assets are pending currently. We're moving the iterator that provides information about how many requests are currently in pending state. So we don't have to reiterate over that same pending request once again. And we're also doing all this stuff related to modifying, pushing liquidity, calculating fees, etc., etc. Yeah, it's quite complex. I do recommend you to read the docs, the both like Mellow docs and inline docs, which are in the interface of this contract. Yeah, like we have this information here, and also like with the specifications of the functions itself. And the last one, quite simple contract, is a redeem queue. Here we use not fenvic3, but just a prefix sum. The only restriction here that arises that after creation, user can no longer cancel this request. So that's why we don't have this functionality for canceling requests. But due to that, we have an ability to create multiple requests for multiple pending redemption requests for the same user. So here the process is quite similar, almost the same. Let's go to the handle report implementation directly. Once again, we are getting information about which reports we want to handle with this price, with this Oracle report. Based on this, we calculate the amount of shares that corresponds to this like interval of the requests, and so on and so on. And based on this, we calculate the amount of assets that needs to be pulled from the vault to this contract to actually handle like this withdrawal demand for users. We have lots of different auxiliary variables implemented here just to track all these balances, but nothing too hard. Once the report is handled by this function, we also needs to, the curator also, or like any other trusted entity, needs to call the handle batches function to actually pull liquidity from the vault to this redeem queue. This is made in this way to allow curator to spend some extra time on unwrapping liquidity from, I don't know, let's say this deposit queue works with native Ethereum, and currently on the balance of the subvaults we only have wrapped Ethereum, and we do not have any functionality to unwrap it automatically using our hooks. Then in this case, curator could take some time to actually unwrap all the wrapped Ethereum into Ethereum, and after that he can call handle batches function to actually redistribute these assets across users in the system that request these redemptions before. Yeah. Okay, so for claim function, it's quite simple. We just iterate over timestamps, and we claim only claimable assets. This function is idempotent, so if there is no such, if the request is not yet claimable due to this logic, or due to there are no Oracle report yet, then we just skip this pending request, or if the requests were already claimed, then that's it. And after that, we just transferring all the pending assets to the user in one transaction, in one call. Sorry. For redeem side, it's quite simple, I believe, quite similar to deposit function, where we just burn the shares from the balance of the user. We calculate the redemption fee that will be applied to the user upon this redemption request, and that's probably it. We're doing quite the similar thing here as well, here to comparing to what we're doing in the deposit queue, but it's quite simpler because we're no longer using this fenvic3 implementation. Well, I guess that's pretty much it. Okay, the last thing that we have in the system is a transfer library that has a specific placeholder for Ethereum. Well, it's not the case for I don't know, Polygon, where we have Pol token, previously Matic. We don't really care because we can just say that the address of the Matic or Pol token that we will transfer in the system are marked as this Ethereum here. We're okay with this. So yeah, that's the point. Yeah, we also have a few hooks here. Not sure that we need to go through them, but basically for redirecting hook, we just redistribute liquidity based on the limits across all the subvaults. For light deposit hook, we stake 3 assets like Ethereum, wrapped Ethereum, staked Ethereum into the wrap staked Ethereum, and yeah, I believe that's it for this hook. We also have a hook for redemptions. This hook iterates over subvaults and pulls liquidity from subvaults to vault address to make it claimable for withdrawal queue. Yep, that's probably it. I'm not sure that we have anything else to discuss. Okay, we also have a symbiotic strategy contract, which is out of scope because it just is an example of how we can implement strategy contracts that will do the same things as Curator do. Yeah, that's probably it.
Okay, cool.
Stop sharing.
Yeah, thanks, Andre. I think that was super useful. I think we have 400, people watching us on this live stream. So this part is for the questions. So please feel free to ask questions in the Twitter, or if you're watching this in the recording, we have a Discord channel where Andre can answer the questions actually. Yeah, to sum up, we have a competition live for the next 2 weeks. We started yesterday. It's 70K in rewards. And yeah, essentially, this is very interesting as you've seen, new Mellow flexible balls. I would wait for maybe a couple of minutes if we have any questions here on the stream. Otherwise, I think that's pretty much it, right, Andre?
Yeah, absolutely.
Yeah, I mean, I think we started yesterday. This is the second competition for Mellow. Super excited about this. When are you guys planning to launch this?
I believe it's the third
Yeah.
one actually.
Yeah, the third one. Yeah. When are you guys planning to launch this flexible vaults? By the way,
I think in a month or so we'll start launching these vaults on mainnet already.
nice.
Yeah, the flow will be quite complex there. But yeah, I believe we will start launching any actual products closer to the end of the next month or so. So yeah.
Yeah, cool. Yeah, I think that we don't have any questions here at Twitter, so we'll be looking forward to seeing your questions and talking with Andre in the Discord. So if you want to join the competition, please go to Sherlock.xyz competitions and join the competition so you can be in the Discord thread with Andre. Thank you very much, Andre, for this deep walkthrough. That was really great. And yeah, looking forward to seeing you in the competition, and happy hunting.
Thank you guys. Yeah. Eager to see your reports and issues.
Right. Thank you guys.
Bye.